Okay, so today we are going to be looking at matrices and systems of equations. And I would like to mention big thank you to MIT OpenCourseWare for all of the material that I am presenting. I would definitely recommend watching the lectures. The professor, Dennis Arrow, is very good. He's a professor in topology, but he lectured in 1802 there. So let's first look at matrix. Let's start with matrix multiplication. Okay, first let's look. Well, where does matrix multiplication come up, and what does it mean when it comes up? So often I'll just say often there is going to be a linear relationship between variables, and we could actually use matrix multiplication to introduce a change in coordinate system. So I'll give a general case here. So actually, so we're relating these two sets of points, the x1, x2, x3, with u1, u2, and u3. And basically, what we are doing is we are redefining the unit vectors in this new world, the u world, in terms of our old world, this I hat, j hat, and k hat world. And I'll explain that in a second. I'm just gonna finish writing this down. So of x3, then x1 plus x2 plus 2x3. Okay, so basically what we're doing, right? We generally, just about everyone in the world chooses an I hat, j hat, k hat system. And the unit vector in the I hat direction is going to be 1, 0, 0, or we could actually, to make a little bit more sense of this, it would just be x1. It would be x1 plus 0, x2, x1 I hat plus 0, x2 j hat plus 0, x3 k hat, because it's not in the j hat or k hat directions. So that's going to be our vector component in the direction of I hat. And then we're going to have, and it's going to be scaled by x1 because that's what we are choosing originally. We're choosing we're choosing some kind of scaled version of I hat, j hat, and k hat, and that is basically what we're just defining as a vector, the vector x1, x2, x3, because it's just x1 I hat plus x2 j hat plus x3 k hat. So that's basically just a normal vector in our quote-unquote normal coordinate system. Then here we're going to have x2 j hat, and then up here we'll have some other vector one-dimensional, because it's only going along one component of these I hat, j hat, and k hat. So, and this is just in the k hat direction. But now we're going to introduce these new vectors, or this new vector u1, u2, u3, and this coordinate system with u is going to redefine the unit vectors in terms of these old vectors that we had in the I hat, j hat, and k hat directions. And I would try to sketch a picture, but it would get very messy and tough to understand. But basically, this is a change in our coordinate system, and we can represent this with matrix multiplication. Actually, if you want to get a good visual on this, I would certainly recommend 3 Blue 1 Brown's video on the change of coordinate systems. In their Essence of Linear Algebra series, is a very good video. So how can we represent this as matrix multiplication? Okay, so we can write this as 2, 3, 3, 2, 4, 5, 1, 1, 2. and we can multiply it by x1, x2, x3, and it's going to be equal to u1, u2, u3. So we have our original vector here, and we're doing some operation on it, some transformation in the plane, or in this three-dimensional coordinate system that we have, the I hat, j hat, and k hat. We do some transformation with these numbers, so then it redefines, and we get new vectors, and then that is what the u1, u2, and u3 are going to be. And you can see now, so if we do the matrix multiplication, and I'll just do it here and explain how I did it in a second. So if I do the matrix multiplication, you would actually end up getting that, because when we have matrix multiplication, we're going to look at the first row of the first matrix and the first column of the second matrix, and we're going to multiply them to get one thing. So that's going to be, and we're going to take the dot product of them to get that first entry in our new matrix. So it's going to be the dot product of 2, 3, 3, and x1, x2, x3, and that's going to be u1. As you can see, that's exactly how we defined it up here. And then you're going to do the same with the second row. So we're going to have 2, 4, 5, the dot product of that with x1, x2, x3. You can see that's exactly what we have up here defined as u2. And the same thing with 1, 1, 2, and x1, x2, x3. That is what we have defined as u3. So basically what we're doing here is we are taking this original vector x1, x2, x3. We apply some, so this is a very important use of matrix multiplication. It is commonly used for transformations. And I'll give another example of that in a second with rotation. But this transformation, we're transforming x1, x2, and x3 such that we can define some new vectors u1, u2, and u3. And once again, to get a more visual understanding of this, I would recommend watching 3 Blue 1 Brown's video on it, because just showing it and not really drawing everything out might not make as much sense as if you saw it. So now let's actually understand what matrix multiplication is, and hopefully this is mostly review. So we can multiply some matrix, so these are going to be the dimensions of the first matrix, m by n. So some m by n matrix, that's the rows, the m is the rows and the n is the columns. And we're going to multiply it by some p by q matrix. So some p rows by q columns matrix. And we can only multiply these two matrices. We'll call this matrix A. And we're not actually, this is not defining the matrix like this would be a matrix. This is just defining the dimensions of the matrix. So we have A is an m by n matrix, and B is a p by q matrix. We can only do the matrix multiplication of A times B if n is equal to p. And why is this? Well, let's see it with an example real quick. Let's look at, say we have a 2 by 2 matrix, and then we have I'm just going to make this really easy, all ones. And then we have a 2 by 1 matrix, and we want to multiply the two. Well, as I was saying before, what we're going to want to do is we do the first row, so the two entries in the first row, and then we take the dot product with the first column. But we can only do this if the number of entries in the first row, which would be the same as the number of entries in any row, since it is a matrix and it's not some arbitrary shape, it is a rectangle. So since it is going to have 2 entries in the first row and 2 entries in the first column, then we can multiply the matrices. And for the first entry, so that entry, it'll be the dot product of 1, 1 with 1, 1. So that's just going to be 1 plus 1 is 2. So we're going to get a 2 there. And then we can do that out, and we can end up getting a matrix. But as you can see, we can only do that if the number of columns in the first matrix, which is the n, is equal to the number of rows in the second matrix, which is the P. And the resulting matrix that we get from doing the multiplication of A times B is has dimensions of M by Q. So for this, we have here a 2 by 2 matrix, and then here we have a 2 by 1 because it has 2 rows in one column. So that means we should get a resulting 2 by 1 matrix because that's the M and the 1, that's the Q. So we only need to compute one more value here. Let's see. So we're going to take that second row now of the first matrix and take the dot product of that with the only column. We'll just do the only column again because it's the only one, so we can't go over again. And now what we're going to get is 2 again because it's just 1 times 1 plus 1 times 1. So that would be the resulting matrix from our matrix multiplication there. All right. So say we have a 5 by 3 matrix and we want to multiply it by a 3 by 2 matrix. What is the resulting matrix going to be? Well, these we can see this are the same. We have the columns of the first one, 3, is the same as the rows of the second one, 3. So we know we're able to multiply them. So now we're just going to have, as stated before, it's just going to be that M times Q, the rows of the first one by the columns of the second one. So it's going to be 5 by 2. But here's where things get interesting. What if we were to reverse these? What if we instead have a 3 by 2 matrix and we multiply it by a 5 by 3 matrix? Well, as you can see here, the N and the P, 2, is not equal to 5, so we actually cannot do this. And that's where we see an important property of matrix multiplication, which is that matrix multiplication is not commutative. Oops. Meaning that if you have a matrix A times B, it is not always, it could in some specific cases be equal to, but it will not always be equal to a matrix B times A. And that is very important to remember. So I will put that in the box for now. All right. So I said before that matrix multiplication signifies transformations. Well, let's quickly look at one example of that. We'll define a transformation matrix R to be equal to 0, -1, 1, 0. And what this is going to do, so if we apply this to some other matrix, what it's going to do is it's going to rotate the vector that matrix symbolizes. It's going to rotate it by 90 degrees counterclockwise. So let's look at something real quick. Let's look at, say we have, actually let's look at the general case. So the general case is where we will define we're going to define our coordinate system. So this first column is going to be the x coordinate and then the y coordinate of our first, this is just in 2 dimensions since we're just going 90 degrees counterclockwise. It's just in 2 dimensions, which is why it's a 2 by 2 matrix. But with this first column, we want to define our first, we want to define I hat, which is one of the 2 basis vectors that we have in our commonly used 2-dimensional system, I hat and j hat, and we're going to define that in the xy plane as x equals 1 and y equals 0. Now, if we had some other unit, maybe say we had, I don't know, some m hat and some l hat with different, we could define these as different, different combinations of x and y. So m might be like x equals 1 and then y equals 1, so the vector 1, 1, and then l could be 1, -1. But here, obviously, that doesn't have any real-world application because we're never going to do that. So let's just look at the simple I hat, j hat case. So I hat we're going to define as 1, 0, which is what we will always define it as. That's the unit vector in the I hat direction, in the x direction. And then j is going to be 0, 1 because we have an x component of 0 and a y component of 1. And now we want to multiply these two matrices. And what we're going to get is pretty interesting. So let's multiply these two. Some more good practice of matrix multiplication. And we know that we can multiply these because they're both 2 by 2 matrices, meaning that the columns of the first one, if we multiply, we're going to multiply R by this. We're going to apply some transformation to this. Remember that it's not commutative. So generally, we're going to have the matrix that we're applying the transformation to at the end all the way to the right, and the transformations being on the left. So we're going to have R, so we have R here, 0, negative 1, 1, 0, and we're going to multiply it by 1, 0, 0, 1. And if we do this, so first let's do first row, first column, dot product, 0 times 1 plus negative 1 times 0. So that's going to go in the top left corner, and that's going to be 0. And another way to see, I'm writing quite on an angle, let me fix that. So we're going to get 0 there. And another way you can see where that entry is going to go is almost like the overlap of where this row, so you have the first row and the first column, and the first row and the first column will overlap on that top left. So therefore it's going to be in the top left that this new entry is going to go in the new matrix, which, as we can have seen before, we have the rows of the first one is 2 and the columns of the second one is 2, so it's going to be a 2 by 2 matrix that results from this matrix multiplication. Now let's do the next one. So we have the first row and the second column, so 0 times 0 plus negative 1 times 1 is going to be negative 1. Now we're going to have the second row times the first column, 1 times 1 plus 0 times 0 is going to be 1. Then here we have the second row times the second column, 1 times 0 plus 0 times 1, 0 plus 0, so that's 0. So generally, now let's look at what this is going to do. This is now how we are defining our basis vectors, our basis unit vectors in our new system. So let's look at the first one. So this first one, this is what I hat becomes. It's 0, 1. So I'm going to call this, I'm going to call this I hat prime, and I'm going to call this j hat prime. And I hat prime is going to be 0, 1. So it's going to be in that direction. And j hat prime is going to be negative 1, 0. So it's going to be in that direction. And now we see that this rotated 90 degrees counterclockwise. And if we were, in fact, to put any matrix or any two vectors there in terms of the x and y coordinates of them, and we were to apply this matrix, it would transform those two vectors. It would rotate them 90 degrees counterclockwise. And there is actually a formula for this involving sine and cosines, but I will not go into that right now because that is more of a linear algebra topic. And there are, in fact, many different formulas for many different transformations. So now let's look at matrix inverses. All right. Just remember that AB is not always BA for matrix multiplication. All right. So let's look at matrix inverses. Okay. Well, first of all, by definition, the inverse matrix is going to be denoted by, that's A inverse. A to the negative first means A inverse. It is not 1 divided by A. That is not what it means. It is its own special new matrix. Okay. And in fact, there is actually no such thing as matrix division, so you would not be able to do 1 divided by a matrix A in the first place. So just think about this A inverse as its own special operation, which I'll explain the steps in detail in a moment. So A inverse, by definition, if you have a matrix A and you multiply it by its inverse, that is going to be equal to this is where matrix multiplication actually is commutative. So it's going to be equal to its inverse times itself, and those both are going to be equal to I, and I is the identity matrix. And actually, in the last example, was an example of the identity matrix, where we had, remember when we defined the I hat as 1, 0 and the J hat as 0, 1? That was actually the identity matrix, and that's why it's the identity matrix, because it's the basis of our coordinate system. So, properties of I hat you might have also seen when we multiplied that matrix, that counterclockwise transformation matrix, by this, we got the exact same original transformation matrix out. That was the output of our computation. So that is actually a very important property of the identity matrix, and it is, so this is the identity matrix. And an important property of the identity matrix is that if you multiply any matrix by I, it spits out the same matrix. Hence why it's called the identity matrix. It's like multiplying something by 1, but with matrices. Okay. So I am going to make a statement that will make sense once we go through the steps of defining a matrix inverse, or computing a matrix inverse. So A inverse only it'll exist if and only if, or we can just write exists if and only if a matrix A is, we'll just say it's n by n. So that means it has the same number of rows as it does columns, and that is actually generally called a square matrix, which makes sense. It has the same like that. It's basically just a square. All right. So, and you'll see why in a second. So let's just go through the process of finding an inverse matrix. Actually, let me write that a little smaller. Okay. So we have that definition there, and this might take a little bit of room. Okay, I'm going to define what A is over here. We're going to do an example of a 3 by 3 case, but this actually will generalize this method that we're doing to find the inverse matrix will generalize to any n by n matrix, any square matrix. So we're going to have A, well, let's see. We're going to have A be 2, 3, 3, 2, 4, 5, 1, 1, 2. And what we are looking for is A inverse. Okay. First step is something we call minors. And how I like to think of minors is, I like to think of them kind of as mini determinants. So I'm just gonna put in parentheses mini determinants, or like the determinant of each individual entry. So what we're gonna do here is this is just the first step. This is not the final matrix that we're gonna get. So the first operation that we're gonna do to this matrix to get on our way to finding the inverse matrix is taking the minor of each entry. So basically what the minor is it's actually for the top row, it's going to make a lot of sense after we just saw determinants. So basically, for 2, we're going to cancel out that row and that column that it's in, and we're going to take the determinant of what's remaining. So the determinant of that is just going to be 4 times 2 minus 5 times 1. So we're going to get 3. So that new top left entry is going to become 3. The same for this one, so we're going to cancel out that row and that column. Sorry, that column and that row, and we're going to get 2 times 2. And actually, that's an important thing here, that it is not negative, even though it's in the middle. And remember I said like it would split it up and that would make it negative. For minors, it's not negative. It's always just going to be the positive or it's just going to be whatever the determinant is. It's not going to be negative of this determinant like it was when we were defining the cross product. So here it's just going to be, this determinant could be negative, which it actually ends up being here. 2 times 2 minus 5 times 1, that's going to be negative 1. But it's not the negative of that determinant. So I'm writing crooked again. So 3, negative 1. And also A inverse of A will also be the same n by n matrix. So if A originally is a 3 by 3 matrix, A inverse will be a 3 by 3 matrix. And so now we'll do the same thing. I'm just gonna write down what we got here. Okay, and now actually let's look at this. So we're going to, for this one, for the 2 there, on the second 2 down there, so we're going to cancel, or we're just going to look at the remaining numbers once we get rid of that column that it's in and then that row that it's in. And the remaining numbers are going to be, it's going to be 3 times 2 minus 3 times 1. So that's going to be 3. And we're going to do that same process for all of the remaining numbers. And when we do that, we will end up getting 3, 1, negative 1, 3, 4, 2. Okay. And so that's the first step. You take the minor of each number. Second step is what is called cofactors. And basically what you do here is you flip all of the signs in a checkerboard pattern. So I'm just going to write checkerboard here. All right, so generally the pattern is you're going to start with, if we have a 3 by 3, it's going to be plus, minus, plus, minus, plus, minus, plus, minus, plus. If it were 2 by 2, it would be plus, minus, plus, minus. Plus, minus, minus, plus. It is just going to be like an alternating pattern almost. It's going to be like a checkerboard. Like if the pluses were red and the minuses were black, then you would get a checkerboard pattern. But instead, it's just going to be plus and minuses. And here, what you do is that if you have a positive there, you're going to keep the sign that it is. So if it's positive, it's going to be 3. If it's negative, that means you flip the sign. It doesn't mean that it's negative necessarily. Like here, it's the negative of negative 1. So it's just going to be 1. And then here it's positive, so the sign stays the same. So it's still negative 2. Here it's negative. You flip the sign, it becomes negative 3. Here it's positive. It stays as 1. Here it's negative. Negative 1 becomes 1 because you're flipping the sign. And then plus, you keep the sign, so 3 minus, you change the sign, minus 4, plus, you keep the sign, 2. So that is what we're going to get after doing cofactors. All right, third step. We're halfway there. The third step is going to be transposing this new matrix. So transpose. And if you have a matrix A transpose is denoted A. It looks like A to the power of T, but that's just A transpose. And basically what transposing is doing is you're flipping or switching or swapping the rows and the columns. Okay, so this new matrix, you could do it one of 2 ways. You could either first look at the columns and then make it the first column, make it the first row, or look at the first row and make it the first column. So let's just look at the first row. So 3, 1, negative 2, and we're going to make that our new first column. 3, 1, negative 2. Now we're going to look at our second row, negative 3, 1, 1, and we're going to make that our second column, negative 3, 1, 1. Let's look at our last row, 3, negative 4, 2, and let's make that our last column, 3, negative 4, 2. So now this is that matrix transposed, and actually an important property of transposition is that if you have some matrix A transpose transpose is actually equal to A. But once again, that's a little more on the linear algebra aspect of things, not too important for this course. And then now the last step is you're going to, and this is why we need it to be an n by n matrix. We need to finally divide by the determinant of A, the determinant of the matrix. So we already practiced computing that last time, so I'll just go through that quickly. We're going to have 2 times the determinant of this, so 2, and then that's going to be 4 times 2 minus 5 times 1, so 3. So it's going to be 6 is the first thing, let's keep there. Minus, now we have 3, and then a determinant of this, so 2, 2, 4, 5, 1, negative 1, and then we're going to have a 3 there. So that's going to be negative 3, but it's going to be minus negative 3. Lastly, we're going to have 3 times the determinant of this, so 2, 1, so plus 2, 1, so that's 2, minus 4 times 1, so negative 2, so times 3 is negative 6, so plus negative 6, and that's going to be, we have 6, negative 6, those cancel, so it's going to be 3. So, now what we're going to end up getting, this is the final step, we get that A inverse, and I'm just going to write it like this so I don't have to multiply everything and rewrite all of those in terms of thirds and whatnot. It's just going to be 1/3 times this matrix up there. And look at that. That's all there is to it. It's very methodical, so there's nothing too hard about it. Just remember what to do. You can apply it to any case. And if you want to check that your algebra is right, you could always multiply A inverse by that original matrix A and check to see if you get the identity matrix, which would be, for a 3 by 3 case, 1, 0, 0, 0, 1, 0, 0, 0, 1. And in general, for n dimensions, or an n by n matrix, I is going to be, it has 1 down the diagonal all the way, and then zeros everywhere else. So all that's 0, all that's 0, all that's 0, all that's 0. But once again, for this class, we're only going to go up to 3 by 3. So you need to know that, and you'll need to know that identity matrix in 2 dimensions is 1, 0, 0, 1. All right, now let's look at equations of planes. Okay, this might be a little bit of a longer video. Okay, so we want to find, so let's set equations of planes. And I'm going to go a little quickly through this since we've already, it's kind of being a long video at this point. So an equation of the form ax plus by plus cz equals d, that defines a plane. And if we want to find a plane in a specific situation, we can use what we've already learned with dot products and cross products to compute that. So let's look at an example. We want a plane through the origin. I'll call that O, plane through O. Typically, in a lot of cases, the origin is just referred to as O. So a plane through O with a normal vector n equals 1, 5, 10. Okay. How can we do this? Well, we know that if this is the normal vector to the plane, and we choose some point P with coordinates x, y, z, we know that the vector, we could say that the vector OP is going to be defined as x, y, z. We know that this vector, if this point P is on the plane, we're assuming this point P is on the plane, then this vector OP is defined as x, y, z, and the normal vector is 1, 5, 10. Well, what we know is that if this is truly the normal vector, then the dot product of this vector OP with that normal vector is going to be equal to 0. Now you might be able to see where I'm going with this, how we're going to get an equation in that form. If we take the dot product of x, y, z, and 1, 5, 10, we're going to get 1 times x, so x, plus 5 times y, 5y, plus 10 times z. And this is going to be equal to 0 because they are perpendicular vectors. So their dot product is going to be 0. And that is a pretty, one of the more simple cases of finding the equation of a plane because it passes through the origin. So let's look at one that's a little bit more complicated, but not too bad. Let's look at a plane. We're going to have the same normal vector. We're going to have a plane through point P naught. And okay, so we're going to have a plane that goes through point P naught. We're going to find the point P naught to be, actually we're going to give what P naught is. We're going to say that P naught is 2, 1, negative 1. And we want to find what the equation of the plane is for a plane that goes through P naught and has a normal vector 1, 5, 10. So once again, let's choose a point P that is going to be on this plane. We're going to say generally that is x, y, z. Now a vector P naught P, we can define as, so we're going from P naught to P, so it's basically just the final point minus the initial point for each component. This is vector subtraction, essentially, or vector addition, but you're adding a negative. So we're going to have x minus 2, comma, y minus 1, and then z minus negative 1, so z plus 1. Okay. Oh man, I'm writing on the diagonal again. All right, I'll try not to do that. So now we have that vector, the vector P naught P, and it's defined as follows. And once again, now we know that if it has the normal vector 1, 5, 10, that means the dot product of P naught P with that vector, that normal vector n, that is going to be equal to 0. Okay, so let's do this. We have 1, so it's going to be x minus 2 times 1, so x minus 2. Then y minus 1 times 5, so plus, I'm just going to expand it, so 5y minus 5. And then z plus 1 times 10, so it's going to be plus 10z plus 10, and that's going to be equal to 0. All right, now let's just move all of the constants to the other side, and we're going to get that x plus 5y plus 10z is equal to, so we move 10, so that's negative 10, then we add 5, negative 5, then we add 2, negative 3. That's going to be equal to negative 3. And something similar that you can see here is that the coefficients of the x, y, and z are still the x, y, and z components of the normal vector. And that is actually something that is true for all planes of the form ax plus by plus cz, that those a, b, and c coefficients are going to be those x, y, and z components of the normal vector to that plane. And then this constant will just depend on some point, on what point, or what point you're defining that plane to go through. It was originally 0 because we defined it to go through the origin, which was the simplest case, but here it ends up being negative 3 because we define it to go through a point that is not at the origin. That's not with the coordinates 0, 0, 0. Okay. So, let's look at one more. Let's apply instead of dot products, let's apply cross products to this. So, say we want to find the equation of a plane with, or containing two given vectors. So you would be given what the coordinates of these vectors are. So how are you going to do this? First thing is you want to take the cross product of the two vectors. Why? Well, if we have the two vectors, remember if we have two vectors A and B, it's from last time, and we want to find a normal vector of them, that normal vector we can compute, or some normal vector we can compute by taking their cross product, because we know that the cross product of two vectors results in a vector that is normal to the plane containing both of these vectors. So we get some new vector, we'll call it n, and that is perpendicular to the plane containing A and B. So where does this get us? Well, we were just saying how the coefficients, remember the coefficients of the A, B, and C are going to be those components of that normal vector. So now we have what A, B, and C are. And now we just have to figure out what D is. And this part's pretty simple. All you have to do, you can plug in some point on the plane that you know it could be, if the origin's on the plane, you could just plug in 0, 0, 0. And then if the origin's on the plane, that's why you would get 0, because you plug in 0, 0, 0, you get 0a plus 0b plus 0c. That's going to be 0. But essentially, in general, you're going to plug in some point x, y, z on the plane. And once you do that, you can just solve for what d is going to be, because this becomes all numerical. Then you solve for what d is. And that has to be true for some point on the plane, because that equation of the plane has to be true for all points on the plane, obviously. All right, so let's look real quick at linear systems. So let's look at a 3x3 linear system. Okay. We'll just do, once again, general case. So a1x plus, we're going to say, okay, we'll say b1 y plus c1z is d1, a2x plus b2y plus c2z is d2, a3x plus b3y plus c3z is d3. So this is a system of three different planes. So we have an equation of one plane here, we have an equation of another plane here, and we have an equation of a third plane there. So if we want to find in general what the solution to this is, well, what we can do, there are many methods in linear algebra that can get this, but the one that we would want to use for this class is we would just want to take the inverse, because that's what we learned. So we would have that, we know this is going to be the matrices, we have a1, b1, c1, a2, b2, c2, a3, b3, c3, multiplied by the column vector, or the column matrix, x, y, z, and that's going to be equal to the column vector, column matrix, d1, d2, d3. So to find x, y, z, we just multiply each side by the inverse of that matrix, the a1, b1, c1, etc., and therefore that's how we're going to be able to find x, y, z. But if we want to look at what our solutions could look like, so what are some possible sets of solutions to this system? There are going to be a couple different ones. So first one is just going to be a point, and this is if, so let's think about it this way. We have two planes, and we have two planes, one plane there, and we're going to have, oh, this is difficult to draw, but I'll do my best, and another plane like this. They would actually, well, it's not very clear by my drawing, but they would intersect. Let me try one more. They would intersect in a line most of the time, unless they're parallel, they would intersect in a line. So one plane there. Oh man, once again my art skills are letting me down. But these would actually, in fact, this one should be a little more clear. They would intersect in a line. So this is going to be the line that they intersect on. So that's once we have two, right? We have two equations of planes, and if they're not parallel, then they'll intersect in a line. Now, if we add in a third plane, say we have a third plane that just goes, that it's like a plane like that, and then that's like inside of that. Hopefully you're able to kind of see what I'm doing, but it'll just intersect at one point, assuming that no two of the planes are parallel. But now if we do have, say we have two of the planes are parallel and a third one is not parallel to it, then we're going to get so we're going to get a line of solutions. Or could be a line, it could end up being two lines, but we'll have, so line, so the solution would be a line, which would mean that there are infinitely many solutions. And we could also get, say these planes are all just basic, the same equation, like say for example, this first equation is x plus y plus z equals 1, and the second equation is 2x plus 2y plus 2z equals 2. Those are just the same equation, just multiplied, but that literally does not matter because they simplify to the same exact equation, meaning that they're the same plane. And if all three of those planes have the same equation defining them, then they all intersect in that same one plane. So we can end up getting a plane which also would have infinitely many solutions, because we're looking at the intersection. A solution to this would be the intersection of the planes. So there would be infinitely many intersections of the planes because they are all the same plane. And then the last is if all of the planes are parallel to each other, then we're going to get no solution. So no solution. And you can think about this, if you have two planes that are parallel, they're never ever going to touch each other, and then you add another plane that's parallel, that still will never touch the other. It's like two parallel lines will never touch each other. Okay. So now let's use what I will keep the possible set of solutions there. I'll keep that there. So now let's look at solutions, and we're just going to go through a general case here, or general case. Solutions to square systems. And that 3x3 system would be just one example of a square system. Square system would be true for any n by n system. It would be called a square system. So general case is going to be a matrix A times that matrix X, which we would define as, if it were a 3x3 case, it would be the XYZ. If it were 2x2, it would be XY. It would be a column vector, column matrix. And we're going to say that that's equal to B. So what we can do, well, first I'll just do this and then I'll explain if it's even really possible or not in certain circumstances. We're going to say that X, we're going to multiply both sides by A inverse. And if you multiply both sides by A inverse, if you multiply both of them by a matrix, I repeat, you must multiply them all on the same side. So I'm going to multiply them on the left of what we already have here. So A inverse B. You can't say that this is equal to B times A inverse because you're multiplying that A inverse on the wrong side of the B. Because I chose to multiply it on the left side here, I also have to make sure I multiply it on the left side there. So now we have this. So that A inverse times A, that's just going to become the identity matrix. And the identity matrix times X, we know is still just going to be X, because X we did define as a matrix. And we're going to find that X is A inverse times B. However, let's be careful now. If the determinant of A is not equal to 0, this is true. So that checks out, that works. Check, okay. But, and if you may have seen this, if the determinant of A is 0, we can't do this because we cannot take the inverse of A if the determinant of A is 0. Because remember, we have to, at the end, when we're finding the inverse of A, we have to, at the end, divide by the determinant, and we can't divide by 0. So if the determinant of A is 0, either we are going to get that it's a line, a plane, or no solution. So if the determinant of A is 0, we're going to get a point. But if the determinant of A, is not 0, we will get a point. If the determinant of A is 0, we will get one of these three cases, either a line of solutions, which is infinitely many, a plane of solutions, still infinitely many, or no solution. And that's it.